So as I mentioned in the previous screencast, we're now going to talk about conformers and rings. So ring structures that consist of only single bonds are really abundant in nature, and we're showing some common ones that are here. Menthol, for example, is a natural oil that contains a six-membered ring. Androsterone is a steroid, and so we can recognize the steroid with the structure here. It consists of three six-membered rings followed by a five-membered ring. This is diamond. It's one of the hardest substances known. It's got an extended network of six-membered rings. And then we have a five-membered ring in ribose and deoxyribose, which are the primary components of RNA and DNA. So although compounds can exist in rings of any size, what we find is that five and six-membered rings are the most abundant in nature. So 5 and 6 member rings are the most abundant in nature. And so, of course, the burning question that we have is why, right? And so because these are most abundant in nature, that suggests to us that these sizes are particularly stable. Now, this idea is supported by the values of ring strains for various cycloalkanes. And you can see how the values are reported here in table 4.1. Ring strain is just the increase in energy due to geometric constraints on the ring. Okay. And so this increase in energy results in a decrease in stability. Okay, so I want you to remember, if we have an increase in energy, then we're going to see a decrease in stability. Okay. So what we see here is in this table, right, we see what's highlighted here is cyclohexane, and it has no ring strain. That means it's going to be really stable for us. Cyclobutane, which is here, and cycloheptane, so the five-membered ring and the six-membered ring, have a really small amount of ring strain. And then what we're going to see here is cyclobutane and cyclopropane have substantial ring strain. Now, the ring strain values in table 4.1 are, of course, for cycloalkanes, but the trend that we observe for how ring strain varies with ring size can be applied to other compounds that are not just simple cycloalkanes. So let's kind of finish putting some words to this. Because cycloalkanes consist of carbon-carbon single bonds, our friends that we've already talked about, torsional strain and steric strain, are two major contributions to ring strain values. Now, there's a third major contribution to ring strain, and that is angle strain. And that arises when the actual bonds, or the actual bond angles, differ significantly from the ideal bond angles. Okay, so torsional strain, steric strain, angle strain all go into ring strain values. So lots of strain here. Now, one of the questions that you might be concerned with is, how do heteroatoms affect this? So let's do a sample problem. Okay, we are going to rank the following compounds in order from least ring strain to greatest ring strain. Now, notice these are all single bonds, And notice that they are not all carbon. Now we have some nitrogen that are involved here. And so here's some questions that you need to ask yourself. What's the hybridization of the atoms that make up the ring, and how does this compare to the atoms that make up a cycloalkane ring? So what we see here is that for each of these, including the nitrogen, these are all sp3 hybridized. So they're all going to have that same hybridization as those cyclohexanes that we saw in the previous table. Now we will get into later what we do when the hybridization is different, but what we're doing right now is we're just drawing some comparisons, okay? So right now, here we are, this hybridization is the same as the cyclohexanes on the previous slide, table 4.1. Because of this, we expect the ring strain for molecules A through D to depend on the ring size as for the cyclohexanes, okay? Because we've got the same hybridization. So we have rings that are 3 to 6, right? So when we look at this, this would correspond to a 3, that would be a 4, that would be a 5, and that would be a 6. So what we would think then is, okay, well, 6 is going to correspond then to cyclohexane. So B would correspond to cyclohexane, okay? And so that means that B would have the least amount of ring strain. So if you flip, I can't flip back because it'll break up the screencast. But if you flip back, you'll see that cyclohexane has no ring strain. And because this is hybridized in the same way, it's also not going to have any ring strain. So B is going to have the least amount of ring strain. Then the next one that we're going to see would be the 5-membered ring, which would be A. When we flip back and look at the table, then, and I'll have to flip back, so let me flip back in my notes and look at the table, because when we look at A with a 5-membered ring, that value is 27, right? So that's going to correspond to that value of 27 kilojoules per mole, okay? And then the next thing I would do is I would look at the 4-membered ring on the previous table, which would correspond to D, and that would give me 110 kilojoules per mole. And then C is a 3-membered ring, and so that would give me 115.8 kilojoules per mole. So we would use those correspondences and then just rank these. And so A would be next, and then D would be next, and then C would have the most ring strain. So there's the most ring strain, and then there's the least ring strain. So we've ranked these from least to most. Now, let's talk about each one of these rings and why the values of ring strain are what they are. So when we looked at table 4.1, it indicated that cyclohexane virtually has no ring strain. And so the question may be, why is this? Why is cyclohexane so special and that it has no ring strain and therefore it's super stable? Well, cyclohexane has very little ring strain because its atoms are not confined in the same plane, okay? So its atoms are not confined in the same plane. Okay. In its lowest energy, cyclohexane exists as a chair conformation. And that's what you're seeing here. So this is the lowest energy for cyclohexane. And this is called a chair conformation. Okay. And what happens here is the bonds that connect the carbon atoms trace out to a shape resembling a chair. And this is like a lounge chair where if we can imagine here, this is the top of the chair. So let me see if I can highlight some of this for you. Nope, not in gray. That's not helpful. This right here is the top of the chair here. And then these 4 right here are kind of this area here where you would sit your tush. And then this green right here corresponds to the green right there where you would put your feet. Okay. And so that's why it's called a chair configuration. And so what we see here is one atom is designated as the head and then one atom is designated as the foot. Because all the bond angles of the ring are about 111 degrees, that's very close. So it's very close to that ideal bond angle for a tetrahedral angle of 109.5. Right? And so that means the 6-membered ring basically, because of that kind of ideal angle, has no ring strain. It also has little to no torsional strain because all the rotational conformations about the carbon-carbon bond are staggered. So we have essentially no torsional strain because the carbon-carbon bonds are in a staggered conformation. Okay, and so all of those things lead us to cyclohexane being a very stable molecule. So let's look at the other cyclo groups that we talked about. So cyclopentane is relatively stable in something called the envelope conformation. So in the envelope conformation, again, I want to highlight this for you. Right here is the green is the top of the envelope here. And then in blue, these 4 atoms right here are flat, like the flat portion of the envelope there. So 4 out of the 5 carbons lie in a plane, and the 5th carbon is outside that plane. And what we see here is the bond angles range from 102 degrees to 106 degrees in this conformation. And so there's some angle strain, but it's really minimized by adopting that non-planar conformation, by that one kind of flap molecule popping up. And so very, very, very small amount of ring strain. You'll also notice that we've got one that is partially eclipsed. Right, so these two, and it looks funny here, but if we're looking in the Newman projection here, we're looking down this bond, and then there's a bond right here in the back, and so that's what we're looking at, and that gives us a partially eclipsed configuration, which also helps with this really stable configuration. Now, the most stable configuration for cyclobutane is close to square, but it's not quite square, and so it's called slightly puckered. Here we've got interior angles of about 88 degrees, and that's a pretty large deviation from the ideal bond angle of 109.5, and so it's going to leave cyclobutane with a substantial amount of ring strain. So we're going to have a substantial amount of ring strain. Okay, and so furthermore, what we can also see is that each of the carbon-carbon bonds remain mostly eclipsed, and that means we end up with a lot of torsional strain as well. So we end up with some torsional strain there. And so that means that puckers out to relieve the torsional strain. So it's going to pucker to relieve that torsional strain. As you look at this, this is dark here, and so that's trying to give it a 3-dimensional kind of view where this is coming out towards you. Now, cyclopropane is very strained. When we look at this, all 3 angles of the ring are 60 degrees, and the carbon-carbon bonds are the same length. And so those 3 points define a plane. And so it forms an equilateral triangle. And so cyclopropane has more angle strain than any other cyclic molecule that we have looked at. And then the conformations of all the carbon-carbon bonds are fully eclipsed. And so that gives us quite a bit of torsional strain too. So super unstable, lots and lots of ring strain here. So we've compared the different rings, and now we're going to focus in on cyclohexane for a while. Now, as I mentioned before, in cyclohexane, all the 6 carbons are completely indistinguishable, but the hydrogen atoms will occupy 2 distinct positions, okay? And so when we look at this image, here's a plane. Ooh, that's not what I want. I want that. Here's a plane that's shown in blue. This is pointing up, and that's pointing down, okay? And I want you to notice that the carbons alternate up, down, up, down, up, down, okay? So we're alternating positions here. This is a chair conformation, okay? I want you to notice that these red hydrogens, so all of these are hydrogens, but we have kind of this orange color here. Those are, right, axial. And axial are perpendicular to the plane. So honestly, if you can kind of imagine Earth, right? So if you can kind of imagine Earth here, right? And the things that are axial kind of point up and point down, okay? But what we see here is we also have these green bonds that are pointing out, and those are called equatorial, right? And it's because when we view Earth, Earth has an equator. And just like the Earth has an equator, those bonds are pointing out to the side like they're at the equator, okay? So it's like the equator of the molecule. So we can identify these bonds as axial and equatorial. Now, we can, when we have a cyclohexane, it can undergo something called a chair flip. Now, when we look at a chair flip, what we find is that, well, first off, let's talk about experimental data first. Even though these hydrogens occupy different positions, axial and equatorial, they're indistinguishable in most experiments, and that's because cyclohexane is gonna undergo a process called a chair flip. This is also sometimes called a ring flip, depending on what vocabulary you're using. And so what's happening here with a chair flip or a ring flip is you have 2 versions of cyclohexane that are interconverting rapidly. Like we're talking millions of times per second at room temperature, okay? And so what happens here, and we're gonna do this, we're gonna build the molecules, we're gonna do this. You push this little envelope up and it pushes this foot down, and then now it's like you flipped your chair around, right? Where this was the head and this was the foot, and now this is the foot and this is the head, okay? I want you to notice, I want you to track this. Look at everything in orange that we said was axial. Notice when you do a flip, now they're all equatorial, and everything that was axial is now equatorial. So a chair flip is going to convert things that were axial to equatorial, the hydrogens, and vice versa. So converting from one chair conformation to the other is really only a partial rotation about the carbon-carbon bonds. Now, a cyclohexane chair flip doesn't occur in a single step, but rather multiple independent steps, okay? And so here's the process. You start with a chair here, and then what we're gonna do is we're just gonna push these bonds up. And so this part is planar, and this is still sticking up. This is called a halved chair. Then as you kind of push this up more, okay, you end up with a twisted boat for a hot minute, and that's real hard to draw, but there's the twisted boat. Then you end up with something called a boat, where these two carbons are both perpendicular and these four carbons are planar. Then you push this down and you end up with a twisted boat. Then once this is fully down, you end up with a half chair. And then when this is pointing all the way down, we're back to our chair. So again, as you do this, this was the head of the chair, and now this is the foot of the chair. Okay, and so it is twisted. The half, a few things to notice here, right? The half chair twist boat or twisted boat, depending on what you're using, and boat conformations are higher in energy than chair because of added ring strain. So we get some added ring strain there. So I want us to talk about where some of this ring strain comes from. And so I want us to take a closer look into the boat configuration. So here is our boat configuration. What you're going to see here is this carbon right here and this carbon right here are pointing up. And what you end up with is something called a flagpole interaction between the hydrogen atoms on these two blue carbons. So the two carbons that are pointing up, we get flagpole interactions. Now, this is classified as steric strain because those two electron clouds interfere with each other and repel. Now, notice in B here, the two carbon-carbon bonds are in an eclipsed conformation and contribute, so when we look at this, right, in the eclipsed conformation, because they're in eclipse, they're going to contribute substantial torsional strain. Ooh. Okay. And so that's what you're going to see here. Now, all they've done is they've rotated a little bit so that you can see the torsional strain. But in this eclipse conformation, you're going to see torsional strain. Now, despite the strain that develops during the chair flips, the energy barrier is still really small, and it's small enough to allow the chair conformations to do this interconversion pretty quickly. Even though a chair flip interconverts axial and equatorial positions on a cyclohexane ring, it does not allow substituents to switch sides of the ring's plane. So during a chair flip, a hydrogen atom in an axial position on one side of the ring's plane becomes equatorial on the same side. And likewise, equatorial hydrogens on one side of the plane become axial hydrogens on the same side. We are going to do a lab where you're going to see this. So if that was wickety wild to you, do not panic on me. We'll do a lab. You'll see this. It will make it so much better. I promise you that. Now, let's talk about how to draw chair conformations of cyclohexane. When we draw chair conformations of cyclohexane, it would be really cumbersome because we have to draw it so much to do it three-dimensionally using a ball and stick like this, okay? This would be a dash and wedge notation, and that's also a real pain, okay? And chemists tend to be lazy, and so we've devised a shorthand notation for drawing a chair conformation shown in figure 423C here. I want you to notice something. The hydrogens are drawn in here. If you're doing cyclohexane, you must draw in the hydrogens, okay? You must draw that in. Now, working with these structures and drawing these are not trivial. There's a right way to draw them and a wrong way. And so we're in this section, that's what we're focusing on, is how to draw these. So let's look at that a little bit. When you first draw this, okay, you will draw the body like this. And I have another slide for you to how to do this, okay? I want you to notice here that when we draw in the axial bonds, they are going straight up. They are shown here in red. They go straight up and they alternate. Up, down, straight down. Up, straight down. Straight up and straight down. And that's how you draw them. I don't want to see any wickety wild mess like that. That's weird. Do -1. Don't do that. And by the way, you're going to have to draw this, right? So just FYI, these go straight up. Then when we are doing things that are equatorial, these guys alternate slightly up and slightly down around the ring, okay? So this is slightly down, slightly up, slightly down, slightly up, slightly down, slightly up. All of these are equatorial. Axial, straight up and down on the axis. Equatorial, slightly up, slightly down, but pointing out to the sides, okay? Now, when we visualize this, there are a lot of colors here, and I know it's wickety wild, right? I want you to notice that all 6 carbon-hydrogen bonds shown in red here are axial. Okay, so the red hydrogens, those suckers are axial. And I thought that was red, but it's so not, it's orange. But we're going to pretend like it's red. Okay, because there's not orange here anyway. Then each, and these are all parallel to each other, right? Because they're drawn directly up and directly down. Then each equatorial carbon and hydrogen, right, that's shown in brown, purple, or green are parallel to one equatorial carbon-hydrogen bond on the opposite side of the ring. So notice, this guy and this guy, right, when we talk about these, right, those are the brown that we're talking about. And we're saying, look, this right here is parallel to this carbon-hydrogen bond. Right here, parallel. This right here is parallel here. So both of these are parallel. Notice this carbon-hydrogen bond in green is parallel to this carbon-carbon bond in green. This carbon-carbon bond in green is parallel to this carbon-hydrogen bond. This carbon and hydrogen bond in purple is parallel to this carbon-carbon bond. This carbon-carbon bond in purple is parallel to this carbon-hydrogen bond. So the axials aren't parallel to anything, but the equatorials are parallel to other bonds in the ring. So step-by-step drawing of this. You're going to draw the front and back bonds so they are parallel. Then you're going to draw the next bonds in here like this so they're parallel. And then you're going to draw these 2 red bonds in here like this so they're parallel. If you don't draw it like this, if you do some sort of wickety wild like that, that's wrong. Draw it like this. Now, once you do this, you'll have a head and a foot, and then you can draw on the things that are axial, and then you draw on the atoms and bonds that are equatorial. Practice this. We are also going to practice this in class. But again, you're going to need to go through this stepwise fashion to make sure that these bonds are parallel to each other. Okay? So make sure you're going through and that these are parallel to each other.